Welcome to my YouTube channel Modi Mechanical Engineering Tutorials. In this video, I would like to explaining in details onto the cooling curve for binary eutectic alloys. Cooling curve means that will be the representation of temperature with respect to time and which kind of phase is being exist for the binary alloys. So in this video, discussing regarding to the cooling curves, or you can say time temperature curve for binary eutectic alloy. Says from the name binary, so here it will be the two metals, metal A and metal B. So at above the melting point of metal A and metal B, both the metals it will be in the form of liquid. So for the binary metal, any metal you can considering, so at the above the melting point of the both the metals who are into the single phase liquid. So in the phase of the liquid, that will be having a 100% solubility in liquid phase. So here talking about eutectic alloys. So eutectic means liquid phase of the binary alloys that will be solidified with two different solid. So here that will be considering as a solid number 1 plus solid number 2. So in general form of the eutectic alloys, liquid phase at some constant temperature, so here at constant temperature converting into two different solid. So according to this eutectic system, into the solidification process of binary eutectic alloys, so in case of the solid solution material, both the solid metals it will be having a differently distributed. So in technical language, it will be having a total 100% insolubility at your room temperature. That's why it will be form a two different solid like S1 and S2. So in simple way, this case it will be expressed as a both the metals A and B which will be having a 100% solubility into liquid state, but both the metal A and B which will be having a totally insoluble at solid state. So whenever you mix such kind of metals of A and B at higher temperature, so it forms the single phase liquid of A and B. But into the solidification process at room temperature, so it will be forms the two different solid S1 and S2. So one liquid phase that will be converting into two solid phase that will be called as a eutectic system, and that will be specified temperature process. So this temperature it will be eutectic temperature. So by the changing of A and B metal, so that will be changing. So in this video I would like to explaining how the metal A and B that will be transferring from higher temperature to the room temperature with the time temperature curve, and that will be called as a cooling curve. So let us start with the cooling curve of binary eutectic alloy. So x-axis, this one, that will be representing as a time, and this y-axis that will be representing as a temperature in degree centigrades. So at higher temperature, or you can say more than melting point of A and B, so we all know that will be the phase of liquid. So let us see here, that will be the point number A that will be representing as a higher than the melting point of both the metals. So it will be representing over here. So similarly we discussing into my last lecture for the pure metal. So compositions of A and B, that will be into liquid form. Now it will be start the solidification process with respect to time. So at some temperatures, or you can say it will be the eutectic temperature. So that point it will be representing here as a eutectic temperature in degree centigrade. So for A to B phase, that will be making a 100% liquid. So it will be considering as a only single phase liquid. So as we are discussing, at higher temperatures for any metals, both the metals it will be into the single phase liquid, because at higher temperatures all the binary alloys which will be having a 100% solubility. So here it will be considering as a 100% solubility. Once it will be touched at the point number B, what happened? Just you can see. So after point B, both the metals A and B which will be solidified at constant temperature, because just you can concentrate for your eutectic systems. So what it means? 100% liquid that will be solidified into two different solid S1 and S2 at constant temperature. So here at the point number B, that will be representing as a eutectic temperature. So at constant temperature solidification process. But for the case of the binary systems, it will be solidified at constant temperature and it forms the two different solid, because into the solidification of binary eutectic alloy, that will be into the solid state which will be having a totally insoluble with each other. So let us see. For eutectic temperature, all the 100% liquid, it will be start to converting into the solid. So this B point, it will be representing as a solidification starting. Solidification start. So after the B point at constant temperature with respect to time. So up to the point C. So here that will be the representation of the point C. So let's take a look which kind of phase is being generating. So 100% liquid, now it will be converting into the solid at point number B, and this process from converting liquid phase into the 100% to solid. So C point, that will be representing as an end point of solidification process for binary eutectic alloy. Just you can write end point of solidification process. So what happened in between B to C process? So which kind of phase it will be coexist between B to C process? So let us see. Starting from the liquid, so liquid phase it will be remains present in between B to C, because that will be the starting point of the conversion from liquid phase to solid phase. One more things, into the solidification of binary eutectic alloys, as we already discussing, it will be the formation of two different solids. So here that will be S1 plus S2. So 100% liquids with respect to time, now it will be converting into two different solid. So at point number C, it will be forms two different solid. So after point C, what happens from this eutectic temperature to the room temperature? So just you can see, so this one is a point D. So as we already discussing, in the case of the binary eutectic alloys, liquid converting into two different solids. So here that will be the representation as a S1 plus S2. Or you can say in simple way, it will be representing as a 100% solid. But that will be having a two phase, because both the metal S1 and S2. So basically S1 is refers as a metal A and S2 that will be the solid phase of metal B. It might be changed, depends upon the metallic compositions of A and B, but it will be having a totally insoluble with each other. Now I would like explaining about the microstructure at different points of A, B, C and D. So let us see. So for region A to B, so just you can see this region I am talking about. So that will be representing as 100% liquid. So just you can see this one is a liquid phase related with the metal A, and this one that will be representing as a liquid phase of B metal. So here that will be the representation of 100% liquid of A and B metal, right? So up to point B, both the metals of binary eutectic alloys, which will be having 100% solubility and forms a liquid phase, and that will be considering as a single phase liquid. Now talking about B to C phase, and that will be having so many changes in the case of the eutectic alloy. So let's see. So as we are discussing, in between B to C, so B point that will be representing as a starting point of the solidifications. So during the solidification from B to C, or you can say at constant temperature, so 100% liquid, it will be converting into two different solids. So just you can see at initial stage there will be the formation of nuclei. Either that will be made from S1 material or S2, anything it will be possible, depends upon the characteristics of A and B, and rest of the parts that will be still into the liquids at point number B. But once at point number C, what happens? So it will be the totally liquid phase of A and B, which will be converting into S1 plus S2, because at point number C, now it will be converting into the 100% solid, or can say two different solid, because both the metals are insoluble at new solid solutions, or you can say at your room temperatures. So that will be the starting point at point number B. Now I would like to explaining at point number C. So just you can see at point number C. So what happens? So here that will be the formation of two different solid. Then that will be S1 and S2. So let's see. So just you can see at point number C, so here that will be representing as a two different solid. Suppose this orange color that will be representing as a S1, and this green color that will be representing as a S2. So basically that solubility of both the metals, it will be depends upon the Hume-Rothery rules. So if you want to learn these Hume-Rothery rules for the solid solution materials, so you will find a link in my description box. So at point number C, it will be the formation of the two different solids, that will be S1 and S2. So basically this reaction, or you can say this cooling curve, it will be for a binary eutectic alloy. That means what? Liquid phase of the both the metals A and B, that will be transferring into the two different solid at constant temperature. So that temperature, it will be representing as a eutectic temperatures. So now this rule, it will be validated by the Gibbs Phase Rule. And let us see the Gibbs Phase Rule. So Gibbs Phase Rule, that will be basically works for the which kind of parameters that will be responsible for the making a different kind of phase between the higher temperature to the lower temperature, or you can say solidification process. So here we are using the Gibbs Phase Rule. Let us see. So we are using the Gibbs modified rule, and that will be representing as a P plus F, that will be equal to C plus 1, where P, that will be the different phases, it will be exist between the regions. F, that will be the degree of freedoms. C, that will be the component systems. And 1. Why? Because we are only focusing on to the two variables like temperature and compositions, because all that process it will be at your constant pressure. So always we are using Gibbs modified phase rule. So now let us see for the different region of AB, BC and CD. So for region A to B, so let's start from the region A to B. So what happens by the Gibbs phase rule? So here that will be the indication of Gibbs phase rule. So P means that will be the phase. For A to B regions, it will be 100% liquid. That's why it will be the single phase. So 1 plus F, we need to identify C. C means component systems. So here that will be the two component systems, because that will be the case of binary eutectic alloys. So means C, that will be the 2 plus 1. So just you can see F is equal to 2 for A to B regions. So just note down over here F is equal to 2. That means what? Temperature and compositions, it will be changing with respect to time, but liquid phase remains into the liquid phase. Or you can say in simple way, temperature and composition changing without changing the liquid phase. So for A to B regions, it always makes 100% liquid. Now talking about B to C. So for B to C, what happens? P, that will be, just you can see, liquid plus solid 1 and solid 2, because that will be the binary eutectic alloys. That means what? Constant temperature solidification process, and in this solidification process, liquid phase converting into two different solids. So because both the metals, it will be insoluble with each other. So that's why it will be formation of two different phases. So 1, 2 and 3. So P is equal to 3 plus F. C, that will be the two component systems. So 2 plus 1. So F is equal to 0. So just you can note down F is equal to 0. That means what? Constant temperature solidification process. So as we already discussing, in the case of the cooling curve for binary eutectic alloy, 100% liquid phase of A and B at constant temperature, it will be solidified into two different solids. That's why F is equal to 0, not a single variables. So you can say in simple way, constant temperature solidification process. Now for region C to D, once again P plus F, that will be equal to C plus 1. So P means number of phases. So here just you can see for C to D regions, it will be formation of two separate solids. So it will be making two phase. So P is equal to 2 plus F. C means component system, so 2 plus 1. So F is equal to 1, just you can see. So just note down F is equal to 1 means just temperature is dropped down from the eutectic temperature to the room temperature, but it never changes the solid phase because both are insoluble with each other. So F is equal to 1 means only a single variables that will be acting onto the two different solids. So this cooling curve for binary eutectic alloys, which will be also validated by the Gibbs phase rule, or you can say in simple way, in the case of the cooling curve for binary eutectic alloy, that will be representing as a constant temperature solidification process, and eutectic means liquid phase that will be converting at eutectic temperature into two different solids. So these two different solids which will be insoluble in the case of the solid solution theory. So I hope you understand the cooling curve for the binary eutectic alloy. So if you like this, then subscribe and share. Modi Mechanical Engineering tutorials. Thank you so much and keep watching.